the most violent world in our solar system, NASA's Io discovery. When we look up at the night sky, we often imagine calm, distant worlds silently orbiting their stars. We picture frozen moons, quiet craters, and endless darkness. But far beyond Earth, beyond Mars, beyond the asteroid belt orbiting the giant planet Jupiter, there exists a world that shatters that peaceful image. A world so extreme, so explosive, so relentlessly violent that it redefines what we thought a moon could be. That world is Io. Io is not just another moon, it is the most volcanically active world in our entire solar system. And what NASA discovered there has transformed our understanding of planetary science forever. Imagine standing on a surface where the ground beneath you never truly rests, where massive volcanoes erupt continuously, hurling lava hundreds of kilometers into space, where rivers of molten rock flow across alien plains, where the sky itself glows faintly from sulfur and ash. This is not science fiction, this is Io. When NASA's spacecraft first sent back detailed images, scientists were stunned. Instead of an ancient cratered surface like our moon, Io appeared young, scarred not by impacts, but by constant renewal. Volcano after volcano dotted its landscape. Some eruptions were so powerful that their plumes rose higher than Mount Everest is tall. Lava lakes the size of entire countries shimmered across its surface. One of them, known as Loki Patera, is so vast it could swallow large regions of Earth whole. But what makes Io so violent? The answer lies in an invisible force: gravity. Io is locked in a gravitational tug-of-war between Jupiter and neighboring moons. As it orbits, Jupiter's immense gravity stretches and squeezes Io over and over again. This constant flexing generates enormous internal heat, melting rock deep inside the moon. The result is a world that is literally torn apart by tidal forces. Its interior churns, its crust fractures, its volcanoes erupt without mercy. This discovery was shocking because it showed us that a moon does not need to rely solely on radioactive decay to stay geologically active. Gravity itself can be an engine of destruction and transformation. Io became proof that planetary bodies are not static relics of the past. They can be dynamic, alive with energy, reshaping themselves continuously. The violence of Io is not random chaos. It is part of a cosmic system. The material blasted into space does not simply disappear. It feeds Jupiter's powerful magnetic field, creating a glowing ring of charged particles around the giant planet. Io does not merely orbit Jupiter, it interacts with it in a dramatic and energetic dance. It influences its parent planet, and in return, Jupiter's gravity fuels Io's fury. Think about what this means for our understanding of the universe. If tidal forces can create such extreme heat and activity on Io, could similar processes occur elsewhere? Could distant exoplanets and moons be heated by their stars or giant neighbors in similar ways? Could such heating create underground oceans, chemical reactions, or environments where life might one day emerge? Io may be violent, but its lessons are profound. It teaches us that stability is not universal. It reminds us that beauty can exist in chaos. Its surface, painted in brilliant yellows, oranges, reds, and blacks from sulfur and molten rock, is strangely mesmerizing. It is destructive, yet visually breathtaking. It is hostile, yet scientifically priceless. NASA's discovery did more than reveal erupting volcanoes. It expanded our imagination. Before Io, we believed small moons were cold and dead. Io forced us to reconsider. It told us that even in the outer solar system, far from the warmth of the sun, energy can thrive in unexpected ways. And perhaps most importantly, Io shows us that the solar system is far more diverse than we once dreamed. Earth is not the only geologically active world. Mars was not the only volcanic planet. Even a moon, small compared to Earth, can outdo them all in raw, relentless power. There is something humbling about that realization. Our planet feels stable beneath our feet, yet out there is a world that never stops erupting. a world constantly reshaped by invisible forces, a reminder that the cosmos is not gentle or predictable. It is dynamic, it is intense, it is alive with motion. The most violent world in our solar system is not just a dramatic phrase, it is a scientific truth. And through NASA's exploration, we have glimpsed that truth in stunning detail. We have seen mountains formed not by slow erosion, but by explosive upheaval. We have witnessed lava fountains rising into black space. We have observed a moon locked in gravitational struggle, turning pressure into fire. Io stands as a symbol of cosmic power. It challenges our assumptions. It pushes science forward. It compels us to keep exploring, to keep questioning, to keep sending our instruments deeper into space. Because every time we dare to look beyond our world, we discover something unexpected, something that shakes our understanding, something that reminds us that the universe is far more dramatic than we ever imagined. And among all those discoveries, few are as fierce, as astonishing, and as unforgettable as Io, the blazing, erupting testament to the raw violence that exists within our own solar system. Io is a moon shaped by fire and powered by gravity, a world where the forces of physics reveal their raw intensity in ways that challenge everything we once assumed about small celestial bodies. When we imagine moons, we often picture silent companions drifting quietly around their planets, scarred by ancient impacts and frozen in time. Io defies that expectation completely. It is not silent, it is not frozen, it is not still. It is a world in constant upheaval, where molten rock surges from the interior and the surface is endlessly reshaped by eruptions of staggering power. At the heart of Io's fury lies gravity, not the gentle pull that keeps our feet on Earth, but a relentless, crushing force generated by Jupiter, the largest planet in our solar system. Jupiter's immense mass exerts extraordinary tidal forces on Io. As Io orbits, it is stretched and squeezed again and again, like a ball being compressed and released. This constant flexing generates internal friction deep within the moon's core. That friction produces heat, enormous amounts of heat, enough to melt vast regions of rock beneath the surface. This process, known as tidal heating, transforms Io from what could have been a cold, dormant moon into the most volcanically active world in our solar system. Hundreds of volcanoes dot its surface. Some are constantly erupting, while others awaken unpredictably with explosive force. Lava fountains rise high above the surface, sometimes reaching hundreds of kilometers into space. Rivers of molten rock carve new pathways across plains of sulfur and basalt. Entire regions are resurfaced in cycles of destruction and renewal. The power of gravity on Io demonstrates that heat does not always come from proximity to the sun. Io is far from the sun compared to Earth, yet it burns with extraordinary intensity. The source of its energy is mechanical rather than solar. Jupiter's gravitational dominance creates a cosmic engine inside Io, converting orbital motion into thermal energy. This discovery reshaped scientific understanding because it proved that moons do not need thick atmospheres or radioactive cores alone to remain geologically active. Orbital dynamics themselves can generate enough energy to sustain global volcanism. Io's surface tells the story of this relentless activity. Unlike our moon, which is covered in impact craters that have remained largely unchanged for billions of years, Io has very few craters. The reason is simple. Its surface is constantly renewed. Lava flows bury old scars. Ash deposits cover ancient features. The landscape is young in geological terms, perpetually refreshed by fire. Mountains rise not from tectonic plate movement like on Earth, but from intense internal pressure pushing the crust upward. Vast lava lakes shimmer in enormous calderas, glowing with heat against the cold darkness of space. Among these features is Patera, one of the largest and most powerful volcanic structures in the solar system. It is not merely a volcano, it is a massive lava lake so expansive that it could dwarf many terrestrial regions. Observations have shown that its surface periodically overturns as cooled crust sinks and fresh molten rock rises beneath it. This churning motion illustrates the dynamic nature of Io's interior, a place where rock behaves almost like a liquid ocean of fire. The interplay between Io and Jupiter extends beyond heat generation. As Io's volcanoes erupt, they eject material into space. Sulfur dioxide gas and other volcanic particles escape Io's thin atmosphere and become ionized by Jupiter's powerful magnetic field. This material forms a glowing plasma torus encircling the giant planet. Io does not simply orbit Jupiter passively, it contributes to its environment in measurable and dramatic ways. The moon and planet are linked in an energetic exchange, bound together in a gravitational and electromagnetic relationship that fuels continuous transformation. Understanding Io's activity has broader implications for planetary science. If tidal heating can create such intense volcanism on Io, similar processes may operate elsewhere. Other moons in our solar system, such as Europa and Enceladus, also experience tidal forces. In their cases, internal heating may maintain subsurface oceans beneath icy crusts. This realization expands the potential for habitable environments beyond Earth-like planets. Worlds once dismissed as frozen and lifeless may, in fact, conceal dynamic interiors warmed by gravitational stress. Io's extreme environment also highlights the diversity of geological processes in the cosmos. On Earth, volcanic activity is driven primarily by plate tectonics and radioactive decay within the mantle. On Io, there are no tectonic plates shifting across a global network. Instead, tidal flexing dominates. The moon's entire structure responds to Jupiter's pull. Its crust cracks under stress. Magma finds pathways upward. The cycle repeats endlessly, reshaping landscapes in relatively short spans of time. The colors of Io reflect its volatile nature. Bright yellows, oranges, reds, and whites stain its surface, created by sulfur compounds deposited from volcanic plumes. These colors make Io appear almost surreal, like a painter's palette scattered across an alien world. Yet beneath the beauty lies violence. Temperatures near active lava flows can exceed those found in many terrestrial eruptions. The contrast between vibrant appearance and destructive force embodies the complexity of planetary evolution. Io stands as a reminder that small worlds can harbor immense energy. Size alone does not determine activity. A moon smaller than Earth's can surpass entire planets in volcanic intensity when subjected to the right gravitational conditions. This insight has influenced the search for exoplanets and exomoons beyond our solar system. Astronomers now consider tidal heating when evaluating distant systems. A planet orbiting close to a massive star or a moon orbiting a giant planet could experience similar internal heating. Such processes may shape atmospheres, surfaces, and even chemical pathways associated with life. The discovery of Io's violent character required technological courage. Spacecraft such as Voyager, Galileo, and Juno provided detailed imagery and measurements that revealed the extent of its activity. Without these missions, Io might have remained a distant point of light, its fiery reality hidden from human understanding. Exploration transformed speculation into evidence. Images of erupting plumes and glowing lava lakes redefined textbooks and expanded humanity's sense of cosmic possibility. Io is a testament to the power of gravity as a creative and destructive force. It demonstrates that celestial mechanics are not abstract equations confined to theory, but active processes shaping real worlds. The gravitational dance between Io and Jupiter generates heat, fuels eruptions, sculpts mountains, and feeds magnetic fields. It is a system of continuous motion and transformation. In observing Io, we witness a moon that refuses stillness. A moon forged and reforged by fire. A moon whose identity is written in eruptions and whose energy comes from invisible forces stretching it from within. It challenges the assumption that stability is universal. It proves that even in the cold outer reaches of the solar system, extraordinary activity can flourish. It stands as a blazing example of how gravity, when amplified by scale and proximity, can become an engine powerful enough to reshape an entire world again and again without rest. Violence that redefined planetary science is not an exaggeration when we speak about Io. Before its secrets were revealed, the prevailing assumption was that small moons were geologically dead, frozen relics of early solar system history shaped primarily by ancient impacts and left unchanged for billions of years. Activity, we believed, belonged to large planets with thick atmospheres or substantial internal heat. Io shattered that belief with explosive clarity. When the first close images arrived from spacecraft observations, scientists expected to see craters layered upon craters, a quiet surface preserving the memory of cosmic collisions. Instead, they saw something entirely different. Vast plains of sulfur, towering volcanic plumes erupting into space, and landscapes seemingly too young to have endured the age of the solar system. The absence of impact craters was the first shock. It meant Io's surface was being renewed so frequently that old scars were erased. Renewal at such a scale required a tremendous source of energy. That energy came not from the sun, nor solely from radioactive decay, but from tidal forces. Jupiter's immense gravitational pull constantly stretches and compresses Io as it orbits. This repetitive flexing generates internal friction, producing heat so intense that it melts rock beneath the crust. This process, tidal heating, was known in theory, but Io provided undeniable dramatic proof of its power. It demonstrated that gravitational interactions alone could fuel extreme geological activity. The implications were enormous. Planetary science had long categorized worlds into active and inactive bodies based largely on size and internal composition. Io introduced a new variable, orbital dynamics. A celestial body's relationship with its neighbors could determine its geological fate. Proximity to a massive planet could ignite a small moon into volcanic fury. Stability was no longer assumed. It became conditional. Io's volcanoes are unlike anything seen elsewhere in the solar system. Some eruptions propel material hundreds of kilometers above the surface, forming umbrella-shaped plumes that rise and fall in spectacular arcs. Lava temperatures exceed those of many terrestrial eruptions, suggesting ultramafic compositions and extraordinary internal heat. Entire regions are covered in frozen sulfur dioxide, constantly replenished by fresh deposits from active vents. The scale and frequency of these eruptions defied expectations and forced scientists to reconsider models of heat transfer and magma dynamics. One of the most profound shifts in understanding involved resurfacing rates. On Earth, geological change can be slow and gradual, though punctuated by dramatic events. On Io, change is relentless. The surface is transformed over comparatively short timescales. Lava flows spread across plains, new vents open, and volcanic deposits accumulate rapidly. This level of dynamism challenged assumptions about the lifespans of geological features on small bodies. The discovery also influenced thinking about other moons. If Io's activity was driven by tidal forces, what about Europa, Ganymede, or Enceladus? These moons also experience gravitational interactions with their parent planets. Could tidal heating sustain subsurface oceans? Could it create environments where chemical reactions occur in liquid water beneath icy shells? Io's violence indirectly strengthened the case for astrobiological exploration elsewhere in the solar system. Beyond our own system, the implications extend even further. Exoplanetary systems often feature massive planets orbiting close to their stars, with moons potentially caught in intense gravitational fields. Tidal heating could make distant worlds geologically active even if they are far from stellar warmth. A planet's habitability might depend not only on distance from its star, but also on gravitational relationships within its system. Io revealed that orbital mechanics can serve as an alternative engine for planetary energy. Io also redefined the concept of equilibrium. Rather than existing in a stable state, it is locked in constant tension. The gravitational tug-of-war between Jupiter and neighboring moons like Europa and Ganymede maintains Io's eccentric orbit. That slight orbital irregularity is crucial. Without it, tidal flexing would diminish, internal heat would fade, and volcanic activity would subside. The entire system operates like a finely tuned mechanism, sustaining chaos through balance. Violence persists because of gravitational harmony. The moon's influence extends outward into space. Volcanic material escaping Io feeds Jupiter's magnetosphere, creating a torus of charged particles encircling the planet. This interaction revealed a complex electromagnetic relationship between moon and planet. Io is not merely shaped by Jupiter, it contributes to Jupiter's environment. This discovery emphasized that planetary systems are interconnected networks rather than isolated bodies. The visual imagery of Io reinforced its scientific significance. Bright yellows and oranges dominate its surface, colored by sulfur and sulfur dioxide frost. Dark lava flows cut across these plains, evidence of ongoing eruptions. Massive calderas, some spanning hundreds of kilometers, mark the locations of active volcanic centers. These features are not ancient monuments, they are active expressions of internal turmoil. Each image returned from spacecraft missions expanded understanding and challenged theoretical models. The violence of Io forced scientists to refine computational simulations and thermal models. Heat flow calculations had to account for extreme localized hotspots. Magma ascent models had to consider low gravity and unique crustal conditions. Tidal dissipation equations were tested against real-world data. Io became a laboratory for extreme planetary physics, offering insights that could not be replicated on Earth. Perhaps one of the most transformative realizations was that activity does not require an atmosphere. Io's atmosphere is thin and transient, primarily composed of sulfur dioxide released from volcanic vents. Yet geological intensity thrives without the thick gaseous envelope seen on planets like Venus. This challenged assumptions about atmospheric insulation and internal heat retention. Geological dynamism proved possible under conditions once thought unfavorable. The shock of Io's discovery was not merely about volcanoes, it was about rewriting planetary expectations. It dismantled the notion that small equals simple. It replaced static models with dynamic systems thinking. It introduced tidal heating as a central concept in planetary evolution. It expanded the criteria used to evaluate activity across the solar system and beyond. Io's example continues to influence mission planning and observational strategies. Future spacecraft are designed with tidal interactions in mind. Researchers analyze orbital resonances with greater emphasis. Exoplanet detection studies incorporate tidal heating into habitability assessments. The ripple effect of Io's revelation continues across disciplines. In redefining planetary science, Io also redefined perspective. It reminded humanity that assumptions can collapse under new evidence. It demonstrated that exploration is not about confirming expectations, but about confronting surprises. It proved that the solar system remains full of worlds capable of astonishing complexity. The violence of Io is not random destruction, but a manifestation of physical laws operating at grand scale. Gravity shapes it, motion fuels it, energy transforms it. In witnessing Io's eruptions and molten plains, we observe the raw mechanics of celestial interaction, a reminder that even in the vacuum of space, forces invisible to the eye can ignite landscapes into relentless activity, reshaping worlds in cycles driven by orbital resonance and gravitational power.